All right, so we are starting off with chapter 15 today. The good thing about chapter 15 is, yes, for those of you at home, I do know my screen is black. I have it on purpose, okay? Chapter 15 has very limited math. Like, I think one math formula for the whole thing. Pretty sure, okay? So I thought you'd be bummed about that. I guess I was wrong. Anyway, I'm just going to tell you, chapter 15, we're going to go fast, okay? Because there's not very much math. We're going to be trucking through this. We're going to get done with this by the end of next week, okay? I know. Which, a couple of reasons why. First reason is we are pretty much minimizing, or at least Mr. Hampton and I are, minimizing or just backburnering, if that's a phrase, lab work. Here's why. Obviously, we've seen a very large increase in the number of quarantines, and there's a possibility that there has been a teacher or two that during group work and stuff like that has actually come in contact with because of the close contact in doing group work. So we are putting that on pause, at least for now, okay? Secondly, we're doing that because what's coming up? Anybody? Thanksgiving, holiday seasons. Okay, so we want to try to minimize that. And actually, since I'm recording, I'm just going to point at you. Black mask. You scoot back a little bit. And to the left a little bit, since you have a little room over there. There we go. So we want to make sure everyone can enjoy that. Okay, we don't want to take any unnecessary risks to everybody if we don't have to. So we are going to have a quiz over the first two sections next Tuesday. Okay, so we're going to spend the rest of this week taking notes. I've got some stopping points here that once we get there, I'll stop for the day. Okay, and then tomorrow we'll pick up where we left off. Tomorrow, after the first section, because these are actually kind of long sections, they're more notes than they are doing like math work, so there's a give and take there. Tomorrow we'll finish it, section 1. Then I'll give you your homework for the first section, and you'll turn it in on Friday. Friday we'll go into section 2, get through about half of that. I'll put the Monday video out, so make sure you check YouTube to finish the notes for section 2. Also, Friday I will be giving you it's like a 15-question review for sections 1 and 2. You can start working on that, finish it off after you watch the video on Monday. Then on Tuesday we'll take the quiz. You'll turn in your review, and then we'll finish. There's only one more section in chapter 15. We'll finish that, and then we'll get the test done before probably the Monday of Thanksgiving week, but that's still a remote day. So it'll be online. You can do that and then be done. Okay. And then we'll also be caught up with Mr. Serbick's class. So we'll all three be on the same track when we come back to finish off the semester. So that's kind of why we're lining everything up this way. Anyway, in chapter 15, we are looking at waves. Okay. Not this wave. Well, you could say that this type of wave, like the Queen does, okay, can you see that, is falling underneath these categories, okay? But we're looking at various types of waves. We're looking at electromagnetic waves, okay, which are very important. We're looking at sound waves. Anything that can fall underneath the title of being a wave. We're going to dissect those concepts in this chapter. So, what is a wave? You'll want to copy these down. Oh. You didn't tell me this projector wasn't on. I was like, why aren't you writing? Okay. Great. Busted that one up. So I'll pause till this gets warmed up.
We kind of went over this last year in 8th grade.
Well, good. So, I mean, and that's the whole point, is you can build upon what you've learned before. So we're going to go a little deeper, most likely, than what you already know. Okay? Oh, yeah, if you're a sophomore, that was 2 years ago. Oh, don't. You telling me. Where if I were sitting in your shoes right now, that would have been 22 years ago for me. Yeah, exactly. All right. So waves are defined as a disturbance that carries energy through matter or space. This energy moves along with the motion of the wave, and no object is actually going to travel with the wave. So if you think about what you see in the ocean or the lake, okay, and you see these waves, okay, you think, oh, this water is just moving around. No, actually what's happening is all those water molecules are having energy transmitted onto them, and it's like a bunch of marbles. Okay, when one marble hits other marbles, they tend to hit others, and it goes on like that. But those marbles oftentimes stay in that same location. Or if you have a beach ball or a leaf, okay, floating on the water, as that wave passes the leaf, that leaf will bob up and down, and after that wave leaves or passes the leaf, it will drop back to its original location. So, I've really come into fishing this year. I don't necessarily use bobbers all the time, but if you are one who uses a bobber, watch it, especially when you first throw it in. As that bobber hits the water, it goes like this, but you notice that it never leaves its location. Okay? It's not necessarily the particles that are moving, it is energy that is moving. So next time you see waves, that's an interesting concept. Water itself is not moving. It's a pulse of energy. And so droplets of water also behave the same way as wave passes. Energy is the only thing that moves along that wave, not water. And really the only reason why you see waves crashing on the beach or on the shoreline is because of disruption of the floor in which the energy has to topple over. That's the only time we really see water move is because there's a disruption. So waves are an interesting phenomenon. Nothing's moving. What you're witnessing is energy. So most waves require what's called a medium. Okay? And a medium is the matter through which a wave travels. Basically, a lot of things are matter. Okay, we've got three main states of matter. Okay, solid, liquid, and gas. Air for the gas. Oftentimes, sound waves are going to travel through air. Okay, think about stereo systems. Water will be the medium for waves, let's say in a pond or an ocean or a lake. And the earth is a solid form of a medium where seismic waves can travel through when we're talking about earthquakes. And so those waves that require a medium to travel through are called mechanical waves. Most waves do fall underneath this category. However, there is a certain type that do not, and those are called electromagnetic waves. And electromagnetic waves are the only waves that do not require a medium to travel. And we're going to see, what constitutes or what falls under the category of electromagnetic waves. So electromagnetic waves, defined as a wave that consists of oscillating. You know what oscillating is? Like this. Okay. electric and magnetic fields, which radiate outward at the speed of light. And these electromagnetic waves, what they're going to do is they're going to transfer energy by changing the electric and magnetic fields of space. Right there. We don't need a medium for electromagnetic waves to travel because it's doing it in space. Light that's traveling from the sun is a great example. In order for that light to get to Earth or any other object, it has to travel through space. Well, space is a vacuum. There is no matter between planets. So it's got to figure the only way that it can get there is through this oscillation, this changing of the magnetic and electrical fields. Radio waves are another one. And we have radio waves here on Earth that can travel through the air, but we also have radio waves that are sent out to satellites and everything in space again. So it's going from one medium to no medium, but it still goes to its direction. Oops, sorry. Okay. So, again, waves carry energy because, going back to our last chapter, because they have the ability to do work. Actually, we skipped 14 because we don't want to do 14. We went from 13 to 15. Okay? So when something has energy, it means it has the ability to do work, and that's our scientific definition. Water waves are going to do work by moving a boat up or down. Because when you do work, you have to move the object. And so as a boat is changing its current position, therefore it is moving. Sound waves do work by vibrating your eardrum back and forth. Although the distance traveled of your eardrum is very small, it's still moved. So sound waves do work by vibrating your eardrum. Now, the energy of the wave is directly correlated to the wave size.
What is eardrum equal? It says vibrating your eardrum and then it equals something.
Yeah.
Really? I think there might be a typo. It's supposed to be sound waves do work by vibrating your eardrum. That's weird. The sound waves do, okay. Oh, no, I'm not on that one anymore. Energy of the waves, again, is directly correlated to the wave size. Therefore, the bigger the wave, the greater the energy, because there's more particles there to impart energy. Now, the energy will spread out as the waves spread out. Eventually, that energy is going to dissipate. We all know what dissipate means. Anybody know what dissipate means? Spread out, okay, yeah. Dissipate more specifically means it's going to decrease, okay? So as we spread out, the energy eventually is going to decrease because when you drop a pebble into a pond, you see that ripple, as you see in this image right here on the top right, you see a ripple go out in all directions. But the further away it gets, the smaller those waves get because energy is dissipating, energy is expanding out. And since you only throw the rock in once, there's no additional energy being put into making those waves. It's a one-time deal. So energy will dissipate or decrease. As you see in this image on the top right, as those waves spread out, the spherical, what we call wave fronts, get bigger. So it's those circles that the waves travel in. So what we see actually is called a wave front. The energy itself is called a wave. The energy spreads out over a large area. So we have a quick video that we're going to show. Well, you know what? I'm just going to put the link in the video. Okay? You can watch it if you want to. I want to get through these notes. If we have time left, I'll come back and watch the video. Otherwise, I'm just going to put the link in the post for this classroom. Okay? All right. So let's dissect the parts of a wave. First, we have the crest. Okay, the crest is the highest point of a wave. So looking at this image here on the upper right here, the crest is that very tip-top point. Okay? Troughs, they're going to be the lowest point of a wave. Okay, much like the trough you have on a farm. Okay, it's the lowest point. So the crest is the highest, the trough is the lowest. The amplitude will be the maximum distance that the particles of a wave's medium vibrate from their rest position. So basically, your amplitude, as you see in this picture right here, with the yellow arrows, kind of the third down for those of you at home, okay, you've got this dotted line, and that's where its rest position is. We call that the equilibrium position. The distance from that rest position to either the crest or the trough is its amplitude. Then we have wavelength, which is the distance from any point on a wave to an identical point on the next wave. So we can measure the distance between crest to crest, its neighboring crest. That could be an amplitude. Or we can even look at this point and measure it to its exact same location on the neighbor amplitude to measure its wavelength. Okay? So we could pick any 2 points as long as they are identical in terms of their location on an amplitude. We can measure their wavelength. So we have different waves when we were talking about this as well. We've got transverse waves. For the wavelength in transverse waves, it is the distance between crest to crest and trough to trough. So these red images here, no wonder. Okay, these red images here, these would be called transverse waves. In longitudinal waves, it is the distance between two compressions or two what we call rarefactions. So the blue coils like a spring, those are longitudinal waves. These compressions where they are really close together, or the rarefactions where they are spread apart. So one of the things we measure when we're talking about wavelengths is period. And that is the time that it takes to complete a cycle or wave oscillations to occur. And the other thing we measure is frequency. This is oftentimes what you hear if they say change the frequency or set your frequency on your radio dial if you listen to regular local radio. It's a number of cycles or vibrations per unit of time. So period is the time it takes for one complete cycle to take, and frequency is going to be the number of cycles or vibrations per unit of time. All right, so vibrations and waves, what are they doing? So waves are related to vibrations, okay? And most waves are actually caused by vibrating objects. Sound waves are produced by a person singing, caused by vibrating vocal cords. Or even as I speak, my vocal cords are vibrating. And those vibrations are having an impact on the air molecules that are around me, which helps determine the sound of my voice, essentially. Electromagnetic waves are caused by vibrating charged particles. And mechanical waves vibrate the medium through which the wave passes. So again, still talking about waves here. There's a concept that we're going to talk about that's called harmonic motion. Okay, simple harmonic motion is defined as a vibration, or also we call it oscillations, that moves an object and exerts a force proportional and opposite to the original displacement force. So if we have a system, much like what we see here on the very bottom, this image down here at the very bottom, we have a mass, which is this dark gray cylinder, attached to a spring. If we were to pull that down from its resting place, that what we call a mass spring system is going to gain elastic potential energy. We call it elastic potential energy because we're talking about a spring, okay? When the mass is released, so as we pull that mass down and it is released, that spring is going to exert a force that pulls the mass back toward its original position. And if friction is ignored, then the form of energy changes in the system, but the total amount of mechanical energy does not change. So again, we go from elastic potential energy throughout this whole oscillation. We go from elastic potential energy to kinetic energy and back and forth. And again, if we ignore friction, then that will go continuously until we have an interfering force like our hand stopping it. But we know that in the real world, we cannot ignore friction. So as that spring and mass are moving, it's creating heat and taking away from some of that initial energy put in and releasing into another form. And we'll stop with this slide here, but we'll talk about that video here a few slides ago. Then we have what's called damped harmonic motion. It's the vibration that is going to dissipate out as energy is being transferred from one object to another. And the amplitudes of the oscillations are going to decrease over time to the damped force. If we have instead of just one mass attached to a spring, we have a series of masses, okay? And those masses are on springs, their own springs, but in between each masses, they are also attached to each other by springs, as we see here, okay? If the mass at the end of the row is pulled, so this red mass over here on the left, if it's pulled and released, the mass will begin to vibrate. And as that mass begins to vibrate, it's going to pull on the mass next to it because of the spring attached between the two. So that one will then begin to vibrate. And that energy and vibrations, they're going to be transferred from one end of the row of mass to the other mass. And as this energy is being transferred from one connected mass, the amplitude of the vibration is going to slow down. Because the masses are connected, or they are damped, they are going to eventually slow them down to where they will cease their motion. So yes, even though there's not a whole lot of math, there's some technical concepts behind waves. Yes.
This slide, I missed a couple of.
Which one is it?
It's the one after the video.
After the video? That one?
Like, yes.
You get it?
Yep.
Okay.
Thank you.
Uh-huh. We'll go ahead and watch this video. I don't think it's very long. Hello.
Hi, it's Mr. Anderson, and this is AP Physics Essentials video 101. It's on mechanical and electromagnetic waves. A good way to contrast these is to figure...
Uh-oh. You know what? I'll just put the link in here. How about that? Okay. Can you go back to the last slide? Okay. Whoop. Okay. Oh, I turned it off. You want to come up here and see it? Actually, while you're doing that, I'm going to just pause. I'm going to stop the recording here.